Now here's a bit of a harder problem to go through, but I think we can do it. Let's try it out together. So what do we have here? Well, we have a wheel, and it consists of 2 rings and 8 rods. The large ring and small ring, and each of the rods weigh 100 pounds for the large ring, 15 pounds for the small ring, and 20 pounds each for the rods. We want to find the mass moment of inertia of the wheel about an axis perpendicular to the screen and passing through point A. So how do we do this? Well, it's not super easy, but luckily for us, the wheels are centered on the origin. And so in that regard, we don't have to do all that much when we're calculating their centroids. However, we're asking for mass inertia around this point A. And so those wheels are not centered on point A. So we're going to have to use the parallel axis theorem for all of this. Okay? For all of this. So let's try it out and see where it comes to. So first off, each ring's center mass is located at the origin. And the rods each have a length of 3 feet. And the center mass is located at 2.5 feet from point O. And in this case, we don't really care what direction they are. They're all, going through the origin. So in that regard, it's all the same. So using the mass moment of inertia data and the parallel axis theorem, remember this is coming from the back cover of your textbook, we can solve for our moment of inertia around the origin. So what is it? Well, for those rings, it's simply their mass times their diameter squared. Sorry, their radius squared. One thing to note here, remember it gave us a mass in pounds, or at least a weight in pounds, and you need to convert that to actual mass units. The unit of mass is the slug, so you need to divide it by 32.2, not by 9.81. That's for the metric system. Then for my smaller ring, it's got a weight of 15, so we turn it to mass, and it's got a radius of 1, so we square that. And then for our rods, now here's where it's going to be a little bit confusing at first. This right here is the moment of inertia for the rod about its axis. Remember, we didn't have to use the parallel axis theorem yet to solve all this. We were just solving for the moment of inertia about this origin. But now these rods, they're not centered on the origin, so we have to work with them differently. So what we do here is we say, okay, it's 1/12 times 20 over 32.2. That's 1/12 times the mass times its length squared. That's its moment of inertia about its axis, about each of these little central points. And then I'm going to use the parallel axis theorem to take that from where it is currently to that point O. So it's a distance of 2.5 feet between their centroid and the actual centroid. So that's the mass times that distance squared. So with that, we have the moment of inertia about the centroid. But this is not the point we asked for. We asked actually point A. So now we're going to use the parallel axis theorem. And here's the glorious thing. This is why we took all of that pain and suffering and getting our moment of inertia about point O. Because then we don't have to worry about anything. To fix it, to take it to point A, we simply have to realize that it's just our mass times the distance between the centroid of this, whatever that is, to where we want. And guess what? Even though we have all of those crazy pieces in there, even though there's all that work, we don't have to take into account that they're all in different locations for those rods. All we have to do is say, well, there's a mass of 100 for the big ring, 15 for the small, and there's 8 times 20 for all those rods. And what's the distance between the centroid O and the point A? It's 4 feet. And we're done. Now there's one little note here. You notice that this says 89.94 and 84.94 up here. I will let you determine which one of those is right. So it may be very well that this should be in 217. But you can determine that. You can go and see, and I'll figure it out later. But for now, that's it. Oh wait, what am I doing? Yes, that's it. We don't want the rays of gyration this time. So we're all done here. Thank you so much for your hard work, and I'll see you all later. Have a wonderful day. Bye-bye.